Hello everybody. Today we will study the topic the calculus of variations. It is one of the important branches of analysis. Suppose that 2 points P and Q are given in a plane. Then there are infinitely many curves joining these points. And one of the questions is which of these curves is the shortest? The answer is very trivial and it is of course the straight line. The second question is which curve will generate the surface of revolution of smallest area when revolved about the x-axis? Answer to this question is not so trivial. Another non-trivial problem is that of finding a curve down which a bead will slide from P to Q in the shortest time. In calculus of variations, we consider quantities like arc length, surface area and line of descent. That depends on entire curve and we seek the curve that minimizes the quantity in question. The calculus of variation also deals with minimum problems depending on surfaces. Let P and Q have coordinates x1, y1 and x2, y2 and consider the functions y equal to y of x and y at x1 equal to y1 and y at x2 equal to y2. So y equal to y of x satisfy these two conditions. They are called the boundary condition. Now we wish to find the function in this family that minimizes an integral of the form I of y equal to integral x1 to x2 f of x, y, y dash dx. So our aim is to find functions y which satisfy the boundary condition and which falls in this family. So our aim is to minimize this integral. We note that length of the curve y equal to y of x is integral x1 to x2 root of 1 plus y dash whole square dx. We already know this formula, that is length of the curve joining 2 points from x1 to x2 is this. Here y dash is dy by dx. Also we know that area of the surface of revolution obtained by revolving the curve y equal to y of x about the x-axis is integral x1 to x2 2 pi y into root of 1 plus y dash whole square dx. Now the third case is the case of the curve of quickest descent, and the integral to be minimized here is integral x1 to x2 root of 1 plus y dash whole square whole divided by root of 2gy dx. Here root of 2gy is the speed, g is the acceleration due to gravity. Hence we have three different values of f occurring in the above mentioned three problems. So we in the beginning of this section I mentioned three problems. So in the three cases we have f in three different forms. One, to find the shortest length. So in that case f takes the value root of 1 plus y dash whole square. In the second case, that is surface of revolution. In that case f takes the value 2 pi y into root of 1 plus y dash whole square. And in the third case quickest descent. In that case f takes the value root of 1 plus y dash whole square by root of 2gy. So in this section we will consider only these three problems and how to find y of x in each of these cases. Next we will study definition of admissible curves. So what are admissible curves? They are the functions, unknown functions y of x that have continuous second order derivatives. That is y dash and y double dash are continuous and they must also satisfy the boundary condition, that is y at x1 equal to y1 and y at x2 equal to y2. Functions of this kind are called admissible curves. Next we have very important result. It is called Euler's differential equation for an extremal. Now we will see what is Euler's differential equation. So our aim is to minimize the integral I equal to integral x1 to x2 f of x y dash dx. Mark it as equation number 1. So suppose that y of x is an admissible curve. Admissible curve means we can consider it as we can consider it as a solution, because this has second order continuous derivatives, and also it satisfies boundary condition. Now admissible curves need not give you the exact solution, but they are the quantities which can be considered as a solution. So first we assume that y of x is one of the admissible curve. Now since y of x gives minimum value, so we are assuming that y of x gives the minimum value of I. Now if you give any disturbance in the function y of x, since y of x give you the minimum value, any disturbance in y of x, that is any change in y of x, will increase the value of I. Okay, if it because y of x gives the minimum value. Okay, so any disturbance in y of x will increase I, and such disturbance are called disturbed function. So we will introduce some disturbed function in the following way. So we construct a disturbed function eta of x such that it has also its second derivative are also continuous, that is eta dash of x, eta double dash of x is continuous, and they satisfy the condition that eta at x1 equal to eta at x2 equal to 0. Mark it as equation number 2. Now suppose that alpha is a small parameter, alpha can take any value, and we construct a new function y bar of x as y of x plus alpha eta of x. Mark it as equation number 3. Now this represents a one parameter family of admissible function. Now we can see that for each choice of eta of x, the minimal function y of x belongs to the family and corresponds to the value of the parameter alpha equal to 0. That is in equation 3, for alpha equal to 0, y bar is same as y of x. Now with eta of x fixed, we have y bar of x is y of x plus alpha eta of x. Now differentiate this with respect to x. So we'll get y bar dash of x equal to y dash of x plus alpha eta dash of x. We substitute this in equation 1. So I of alpha becomes integral x1 to x2. We had f of x comma y dash. So instead of y, we consider y dash, y bar, then y bar and derivative of y bar. So we substitute for f of x comma y bar dash. Now from 3 we have when alpha equal to 0, y bar is same as y of x. Now we have already assumed that y of x minimizes the integral. So we know that at minimum and maximum or minimum value, its first derivative must vanish at that point. That is I dash of alpha equal to 0 at alpha equal to 0. That is I dash of 0 is 0. Now this is a graph. It shows the point, 2 points x1, x2. Then we have eta of x is one of the disturbed function. Then we have constructed the new function y bar of x equal to y of x plus alpha eta of x. You can see that when alpha eta of x is this vertical length, and when it is 0, then y bar and y are same. Now we have the condition that I dash of 0 is 0. We apply this. So first we have to find the derivative I dash of alpha. So here f is a function of 3 variables, so we have to do partial derivative. Integral x1 to x2 dou by dou alpha of f of x comma y bar dash dx. You can use the chain rule here. So dou by dou alpha of f of x comma y bar dash is equal to dou f by dou x into dx by d alpha plus dou f by dou y bar dy bar by d alpha plus dou f by dou y bar dash dou y bar dash by dou alpha. Dou y bar dash, this dy bar dash by d alpha. Here we have a correction. The last term is dy bar dash by d alpha. So the first term, we know x is not a function of alpha, so dx by d alpha is 0. Dou f by dou y bar, then dy bar by d alpha is equal to eta of x. Since we have y bar of x is y of x plus alpha eta of x. So dy bar by d alpha will be eta of x. Similarly, we have y bar dash of x is y dash of x plus alpha eta dash of x. So dy bar dash of x by d alpha is equal to eta dash of x. Now we substitute in I dash of alpha. So I dash of alpha becomes integral x1 to x2 dou f by dou y bar eta of x plus dou f by dou y bar dash eta dash of x dx. Now we have the condition that I dash of 0 equal to 0. So when we put alpha equal to 0, LHS is 0. So integral x1 to x2. Also we know that when alpha is 0, y bar becomes y. And similarly y bar dash becomes y dash. So we get integral x1 to x2 dou f by dou y eta of x plus dou f by dou y dash eta dash of x dx equal to 0. Now we will simplify this equation number 4. We will take only the second integral here. Okay, and we will use the integration rule. So integral x1 to x2. So consider the second integral of equation 4. So integral x1 to x2 dou f by dou y dash eta dash of x dx. So consider dou f by dou y dash as the first function and eta dash of x as the second function. So first function dou f by dou y dash into integral of second, so eta of x minus integral derivative of first, that is d by dx of dou f by dou y dash into integral of second, so eta of x dx from the limit x1 to x2. Now when we put the limit x1 to x2, the first term vanishes because we have eta at x1 is equal to eta at x2 equal to 0. So the first term vanishes. We have only the second term. So it is equal to minus integral x1 to x2 eta of x d by dx of dou f by dou y dash dx. Now substituting the value of the second integral in equation number 4, we get integral x1 to x2 eta of x dou f by dou y minus eta of x d by dx of dou f by dou y dash dx equal to 0. Eta of x is common, take it outside, so we will get integral x1 to x2 eta of x into dou f by dou y minus d by dx of dou f by dou y dash dx equal to 0. Now this integral must vanish for every choice of eta of x. We can take any value for eta of x, and in all cases this integral must vanish. This is possible only when dou f by dou y minus d by dx of dou f by dou y dash is equal to 0, which means that d by dx of dou f by dou y dash minus dou f by dou y equal to 0. This equation is called Euler's equation. This is very important equation. This Euler's equation is an equation this is a differential equation for an extremal. So we have to remember this equation.